Hello and welcome. So you see one screen. It is from Facebook post, and the owner is Tom Nazir. He has written a book on PLC program, on STL language as well as the ladder language, logic. This post is from his, I think, STL structured text ST version 3. And you can see the book ISBN. But I will go through this, the text he has written, the program. This program is controlling the pumps. It has two pumps, actually emptying the pump from a, liquid tank. And then the liquid tank has a level sensor, floating sensor. It's a switch actually, NO or NC. And it has two type of switch. You see the LS1, he has given the comment on the right side here. It's a normally open type. LS1 and LS2 both are normally open, and LS1 is the lowest level to measure, and then LS3 is NC, normally closed type, possibly to detect the overflowing, the tank. Normally closed, the advantage of it is that it is when the liquid is not in touch with the switch, it is actually giving a signal, positive signal to PLC. That means this signal is always connected to the PLC input channel, and when the liquid is not in touch with the switch, PLC getting high signal 1. And in case of two possible scenarios, either the sensor where is disconnected, or the liquid touches the switch. In both cases, the signal will be 0, that is false. In that case, we can actually take precaution measures, like even when sensor is not working, do something else, do like start the pump, both pump, or like high level alarm, or when the liquid actually touches the switch, also the same thing should be in the program. And those two pump to be run, then there is actually requirement that you should run one pump for maybe some condition and another pump in the condition. So alternating two pump in different scenario instead of running one whole pump continuously, because that can heat up the pump body and it will reduce the lifespan of the pump. So better is to install the both two pump and run them alternative, half this time, another half this time. This program is done to do that only. And if you see, it has some variable initialized, two variable M1 and M2. It has, when we start the PLC, it's not starting, pump are not running. Another variable is taken, that is Boolean type run motor, and initialized to 0. Now let's go to this line. If you see here, if not LS1, now remember LS1 is the normally open, so normally not LS1 means there is signal, that is 1 high. Normally open is 0 because it's normally open. If liquid is not there, it's not touching the switch, then the value of LS1 is 0. The input is getting 0. But putting the NOT instruction actually inverts that value to 1. So that means if there is no water, no liquid in the tank, then don't run these two pumps. So no liquid, why to empty the tank? Because it's already empty, right? So that part is doing this. Now LS2 is activated, start one pump. Now one pump is if it is the first time, let's say the tank level is being filled up from another source and the level is going up, and then let's say LS1 activated. Okay, nothing happened because for LS1 we do not have much information. LS1 is to just deactivated, stop the pump. It has nothing to, no logic to start the pump. So LS2 is checked for starting the pump. So if LS2 is normally open, so LS2 level comes, just touching the LS2 and activates the switch. So LS2 got high signal, not M1, not M2. So no motors are running, no pumps are running. Then M1 run. Now this M1 assigned a variable run M. Run M is what? Is 0, like initialize. So that means stop the M1, even though it was not running. Nothing wrong to stop again, and M2 not run M. So that means because run M is initialized to false, not putting before the variable gives opposite invert signal, that is 1. So M2 will start in this scenario. Now the pump alternation is happen. Let's say when the pump 2 starting, okay, it's started the pump and then level goes down a bit, and after that again it moves up, the level filled up again, and then it is touching the LS2. What should happen? The M2 is still running, right? M2 is still running, you see. Now in this scenario, if you see, if not LS2, because the pump is running already, we have started M2, but we have also inverted the variable value. So before starting the PLC, when we start it was 0, but after we got into this condition, we have actually changed the value of this run M variable. This part is run only once. It's just assignment and declaring the variable. This program continuously in every scan of the PLC continues to scan, okay, this part. So when we started the pump M2, it has just entered into this one, but it cannot enter into this condition because of this instruction. M2 is already running, but it's checking for M2 not running, so we cannot look into this now. The level came down and going up again, and then touching the LS2 again. So now look for this instruction when the level is below LS2. After LS2, actually the pump started and the level goes down. So look into this instruction. When the LS2 is not there, M1 and M2 both are running. Now M1 is not running, we know. So you see this condition is not applied anymore. Okay. So where is that other condition when LS2 is not there and M2 is running? We cannot find that. Okay, so motor 2 continue to run, and then motor 2, let's say that level goes up and up and up, and then it touches the LS3. That condition we can find here. See, not LS3. Why not? For LS3 and not instruction before LS2, because they are different signal, different switch. This is NC type. Okay, LS3 NC type means by default when the level is not touching the LS3, the signal of LS3 is 1 high. So when it is touching with the liquid, okay, this floating switch actually activates the LS3. That means the circuit breaks from the live signal. The signal goes actually 0. LS3 goes 0. So putting not in front of 0 actually inverts the 0 into 1. So if then it satisfies the if condition, then M1 and M2 both are true. So that means M2 was already running, and now if the liquid touches the LS3, we actually run both the pump M1 and M2. What is probable situation? If both pumps are running, then emptying is easy and it is faster. So the liquid level expected to go down unless the inlet is fully open and more than the flow of the outlet together. So when outlet flow is more than the inlet flow, the water coming in is less than the water going out, then of course the level can go down, right? So level goes down, and let's say it goes down until middle of the below LS2, I can say. So when the LS2 is no more floating, that is the situation you get this instruction. If not LS2, okay, so it's no more floating, LS2 is no more floating, and both pumps are running, then run M. Now we are actually stopping one pump. You remember we have inverted last time, run M equal to non-run M. So that is before it was initialized to 0. Now the run M variable has 1. So we run M1. Remember this instruction we started M2. We have began the running the pump with the M2. Now this is where we are actually stopping the M2. We are stopping the M2 and handing over to M1. So M1 should be running around, M2 should be stopped. And then we are inverting the variable value again. So now it was 1, and we are putting the not instruction again and initialize the value of run M variable to 0 again. So this level going up and down will continue, and the pump of alternating M2 and M1 and things will continue to happen. So every time the level goes up from the beginning below LS1, when the level goes below LS1, both pumps will stop, and when it's going up, the pump 2 will start from this instruction, and when it hits the LS3, and both pump shall run, and this condition will alternate the pump and start the pump 1 and stop the pump 2, and that thing will continue to happen. Let's see how we can do this in real programming. You can see the 1, 2, 3, 4 is actually corresponding to this program. One is the empty pump tank. 2 when LS2 is floating, going up, and LS3 is when tank is full. 4 is when going down. And someone written here LS2 should be NO, but that's not correct. LS2 is here perfectly fine in this example. Let's just open my computer and so here is my TI portal, and I would like to create a project called pump alternating. Okay, control liquid tank level. So now, hello. Yes. So we have created a project, and now this project is open. Location of folder where my project is saved is this one, and I can go to project view and create my program. So first thing, add a PLC. We can, let's say this one. I would like to take this one, 17. Okay. So first thing first, we will take as it is in the program, but few things we will actually modify. We will use a function, okay, for creating the program. This is our program, and we do not have any IOs for this CPU, so some input and output module is required. We will take 16DI 16DO module and insert in the rack swap number 2, and then open this and create some tag for this. We have address 0.0 to 1.3, sorry, 1.7, and output 0.0 to 1.7. So here, let's say this is LS01, LS02, LS03, and we have to put some instruction comment there. This is low level, middle level, high level. We don't want to use the default tag, so let's create a tag table. We name it something like tank level 01, maybe. We select that tank 01. Okay. And what else we need for input? We do want to take the motor running feedback, even though we have used the motor, for the programming, but the real situation, you cannot use the output in your program. That's not right thing to do. In usual practice, the contactor will have a feedback, okay, from the motor. When the pump is running, the pump feedback you will get from the contactor when the pump is running. So you get something like pump 1 feedback and M2 feedback. So this is we will check for motor running. Okay, this is M1, it's running, M2 running. And then this one is M1, M2. Of course, we want to change the default tag table. So now tank 1 IO list is completed. If you go to tank 1, we have all the IOs listed here. Okay, so let's create another variable called alternating variable for tank 1 pump alternate, and this one I would like to use Mercury variable 1 point, maybe 2.0. The first 2 bytes reserved for some other purpose. I use M 2.0. So that is the run M you see in your example. Run M. If you want to give same name, okay, no issue. We give run M, no, tank 1 maybe, because different things may have different bits to use. This tank has 2 pumps, and let's go to program block. We can use the program in OB1. We can create the program in OB1, or we can use different block to do that. I will use different block. That's first thing first. Better to start organizing from start. So here I would give a name tank 1. I want to create STL, so create STL, and the thing is, you see in the example is this block, this var and in var is within this block, right, in this scenario. But normally that does not happen. We don't use variable value from the that input in the user. Example doesn't show how to call this block and things like that. But anyway, I will show you how we can do that. So here is let's say level 1 ls. Oh, this is OB1. Sorry, we have created a FC1, so we will start programming in FC1. The input thing will be LS1, LS2, LS3, and what else? M1, MB, M1 feedback, M2 feedback, and what else? Input. No more inputs. So output is M1 and M2. Okay. And input output, we have one is called run M. That is the variable we want to connect here, because it is input as well as the output. Okay. So we are checking this at the beginning, and then we are setting as output within the program. So here we want to do the first few line, like stop pumps. So when that we need to stop pump if ls1, not ls1, okay, not ls1 and not ls2, then actually we do not need ls2 here. ls1 is the low level, right? So I need to check both. Then m1 is running. Y is m2 run. Okay, so ls1, why is this Okay. Do I need to bracket it within the bracket? No. Otherwise, gets error. Uh-huh. Let me, if syntax error, if is not correct, it says, so if syntax, because end up is, I have not ended the program yet, sorry, and if something is not right here, what I'm doing is, if then, okay, maybe I can insert some, don't know why suddenly, insert, okay, good that it came. Actually, I can insert some template here. Instruction on bit logic, Boolean logic program production. See. I'm sorry. This is, I was writing STL language instead of ST statement language. That was my I don't know actually. From beginning, I'm talking about STL, and this program, the written program, is not actual STL. Sorry about that. The whole recording, I'm just talking about the STL language. This is a structured text language. It's a high-level language. ST language is different. It's not high-level. This is the ST instruction. If you see, actually, we can write something like this. It's simpler actually, but you need to really understand the mnemonics of this instruction. I'm going to write a program using this instruction. Anyway, so I don't know how I did that mistake. Sorry about that whole thing. If ls1, that this is the end, if ls1 is there, then actually this should be not ls1. Okay, is something like I say an. So if it is not an, okay, an ls1, then stop the pump, like you see this one assignment, this m1 and m2. This is the way it is done, is not actually in the same line. So we have to use this again and again, like again an ls1. So this is missing bit address. So there is no thing as semicolon here. So what is that one? No, nothing is wrong, which is has taken. Normally, we don't use this for separate initialization. One ls1 is checked and both pump can be stopped this way. So this is the instruction. This part is equal to this line. So if ls1 is not there, so ls1 is not floating, stop both pump. And then ls2 switch is floating, then both pumps, if not running, then do this. Okay, so here I would say a ls2. Okay, a ls2 and next line. Okay, a m1 fb. Okay, a m2 fb. So you see this and so this equal to that if logic. So all three are correct. So ls2 is there, m1 m2 not running, then run this m1 m1 with that whatever the initial variable, because when we do the run fb here, the run, I would tell you how to initialize that run in m bit, but hold on for that moment. Okay, I'm sorry about that. Totally messed up. My intention was to write this code. I was always talking about that language, STL. But let's go through this. What it is being done here. If all three are correct, then assign m1. Okay, and this is a difficult thing to actually do the high level programming syntax in STL, because normally you cannot assign value from one variable into other variable in STL language that way, this way. So we have to use some kind of I would say move instruction. How to do this? That's a thing. Just to hold one bit. Oops. Okay. Okay, so this one we can start with the motor. This, compare this. Mm. So let's just go through that program again. Where is that program? It's here. Okay, so let's we have AND of these three, and then we are assigning one variable value into another variable value. And in STL, we can do that using move instruction. But thing is, here we are moving bit. Okay, so bit, moving the bit. We can do that in MCR, using MCR. No, we cannot move this. Yeah, just I checked the. mm, we can do one thing. I have just like the call to another block. Let's create another block FC. Okay, and this one is to let's say pump return script. Okay, so let's change one. Call start or jump conditionally to ACM. See, this is the structure of STL programming. So if this is all true, then we can do something inside here. This is an interesting thing in STL language. How do we do? We can do all these things inside it. So we can write another program within this location. We can initialize value now m1. Let's say m1 equal to that, means we are actually checking that variable a. What we are checking? We are checking this in-out variable, right? A. If this is true, then I assign m1 the value. If it is not true, then 0 will be assigned, right? And then we are inverting the value of the run m. Okay, of course we are also assigning the opposite value of run m. So we can do something like an, then run m equal to m2. Why is this way? The instruction is correct. Why then it is? This is this, and then this is this. And we are also doing invert of an. Run m equal to run m. I do not know why that happened. Okay, so it's maybe editor issue, but notice here I'm assigning the variable value of run m into this m1, just like there, just like there. Run m is assigned into m2, and then not run, so it's the opposite variable value is assigned into m2, and then inverted the value within that variable. So I'm also doing that thing. When it is not true, then make it true. This n is checking for 0. When it is 0, make it 1. So that's how we use n. So this does not make sense, right? If it is true, then make true. It doesn't make sense. So when we are doing an, we are actually inverting the value. And also you see this instruction, they are all opposite, right? And this instruction is jump if not true. That means if this is all not true, then jump here, and after that we do not have any programs and no operation in OP. This program will be skipped when these three conditions are not met. Yes, I think we do not need this block anymore. I just could not figure out at that moment, but now I have the jump instruction thing, so we covered here. Now another, if not ls3, then both should be running, right? Now come to the next here. This program, okay, just make a comment here. This is for one. Stop pump. Okay, we have that instruction. Here, okay, stop pump. And then this one. Okay, this is also not right. I just noticed this because if we use that way, it will be, starting both pump here. Instead, we can use the jump thing again, like if it is not there, JCN, something like _00, okay, and then jump here, _00, and then okay. So if it is not true, that means if level switch is not there, okay, that's this one. Level switch is not there, that means it's not floating, right? When it is not floating, that means low level, then go into this program, assigning this value into 0. So we can actually take some value that is equal to 0. We cannot write something like false and false. We cannot do that, so we have to take some variable here which is always false, and that comes into an interesting configuration in PLC. Here we can that's why I actually left 2 bytes, you remember in the beginning. Here in the properties, we have this clock bit, okay. The system clock, we can enable this clock bit always 0, always 1. See, always 0, M 1.2, 1.2, always true, and this is always false. So we will use something like always false 1.3, and here always false, which is A M 1.3, and it's never going to be true, right? So if it is false, then obviously this 2 will be also false. But yeah, that's right. So a result of logic operation will be 0, right? And then that result of logic operation will be assigned into these 2 instructions to both pump. So this stopped. And if ls1 is floating, then of course this will be skipped here, and then check for ls2. Okay, this is 2, pump 2, and then let's say start M1 and M2. So in this case, we are actually checking for switch, which is ls. We are actually checking opposite, AN M3. You remember M3 is normally close. So AN, sorry, we need to check the feedback. ls3. So let's go to the program, and here it says if not ls3 then run both. So how do you, if this is true, not I mean when it's floating the signal actually breaks, so the PLC gets 0. That's where we are checking this one. So we write this jcm 02, go here underscore 02 and then write p here, and inside this we write the program what to do. Inside this we write you remember, just like we just activated the PLC clock bit, we would use AM 1.2, which is always true, equals to M2, M1, and it's not M2. Okay, this way. Okay, so always true assigned into this bit, this two output. So both should be running when we don't get level switch 3 signal. I hope you're clear now. So what we have pending is this part. If not ls2 and both are running, then we have to switch the run m variable, and this time we are starting m1. Okay, so let's start this. This is very interesting program. We started from that explaining Facebook post, and seems very lot of things to learn from this example. If not ls2, then and both are running, then do this. So we will do something like this. ls2 is not there. Okay, so ls2 not floating anymore, so here an we would write, and not ls2. ls2 is not there, then we use the jcm instruction again, and this time we would use 03, jump to 03 level, and then write NOP instruction. So in this line we don't actually write an instruction, but you can actually want. And this one we are this time we are checking the variable with running variable. Okay, because we are assigning the value of this variable, and it has we have actually last time changed the value of this variable. Okay, so this time we should have one variable and then assign to m1. Okay, and then what else is there? We have assigned m1, and m2 will have opposite value. So we opposite variable of run m assigned to m2. Okay, again this is giving warning for not correctly typing the name. We have to be careful of that. Now if you have done this, we have one thing pending, is doing the same like this, converting the value of this one. So this time it has the run m value 1, making an means actually inverting it to 0. So 0 value will be assigned to this one. So again, it's actually preparing for the next cycle when the m2 will be starting from when the level is going up. Okay, so this thing is complete now, and we have talked about how to initialize this run m, where we are initialized, because we have not done quite what is done in this program. In this example, that variable declaration, because the programming language is different. It's a structured text. Siemens may have called it a different language. It's not STL, it's actually SCL. So that language is called SCL. Okay. Programming in SCL, I do not know why it is called structured text here. Obviously, probably because the IEC 61131 has one programming language called structured text, and that's quite similar to what Siemens called SCL language. So let me show you. Okay. So here, STL, Siemens has STL, ladder, FD, and SCL. So that language you see here in this example is that language, SCL. Okay, this SCL, not, and what I am doing is the STL language. Okay, STL language. So Siemens has other 3 more languages: graph for S7, high graph, and CFC for S7. Interesting. So let's end with that whatever pending. I told you how to initialize this run M, and this run M can be initialized when this block is being called, or how we can do that here. Run this value equal to 0. Actually, you cannot put default variable value here. So okay, so you have to create a restart block, organization block. Okay, it has one block inside this OB organization block. If you go to here, and you see this startup, a startup, and the number is 100. A startup OB will execute one time when the operating mode of PLC changes from stop to run. After completion, the main program cycle OB will begin. So program cycle will start to execute after this. What is this number? 100, startup block. So we click OK and we get one startup block, 100, and we open this one, and we have to write a logic, because you see as per the program, where is the program? Okay, as per the program, the run M should be initialized to false, and also the motor M1 and M2 both should be false. Let's go to this false thing. False thing, how to get false thing? We have always false M1.3. Okay, so we assign the value of false, not this instruction, we use this one, and then we assign to M1. Okay, and M2 use 0.1, and that variable called M2.0. okay, we have named it run M for tank 1. Okay, so always false. Sorry, I have written it in ladder logic. We are doing STL, so we have to change that language to properties, change it to, we do not switch to from ladder to STL. There is no option. So anyway, this should be something like, again, we can delete this, delete, recreate, and this time we select ladder. You see the SCL option is there, ladder. Maybe another day I will show you how to do the SCL, and select the startup SCL, STL, sorry. Open it and write this A M1.3. Okay, A1 always false, right? Remember, so this is Q0, Q0.0, and then again you go to Q0.1, and what is there? M1 2.0. Okay, that run M for tank 1. And how we're going to use this? Okay, we open the Avion, and again we do not want to use it in ladder. Instead we can switch this property. I have FPD again. What we can do, delete it, create again, organization block, program cycle block, and select STL. Open it, and here we write simply call, or open instruction here, program control operation, or very open. Call block. We call the block, which block? Tank 1. And we get all the variable names where we have to assign, the input and output. So remember, we have a tank 1, tag list. So you copy this and go to OB1 and assign each, LS2, and then LS3, and then M1 FP, M2 FP, then M1, M2, and this one tank M2.0. We can write this directly. So now the call to the tank 1 is done, and when the PLC is in run mode, it will call this tank 1 function and go through the program. Okay, so now we have all the variable assigned to the external input and output, and the values will be loaded here. We are assigning the variable value here, the tank internal variable. This is our real input and output side, and this one is the 2.0. So every value is actually mapped to the internal structure of this function. So hope you have liked it and understood the whole point of this video, how you can do the equivalent to that program in STL. So we have done this ST program in STL language, and we have also talked about the different other languages here in this plot. Ladder, FPD, so all languages can be done. Example from the Facebook is in SCL language or structured text. Thank you for your